All right, so what I want to do today is I want to start off with the little bit of technicalities, the Kolmogorov axioms of probability. So there are 3 axioms. These are very reasonable. These will allow us to derive a lot of other things we believe are reasonable. There's some technical blah in the beginning. So we have a sigma algebra, big sigma. The way you should view the sigma algebra is this is a collection of sets that we will assign probabilities to. I'm not going to go into too much detail as to what this is. If I have a finite set, the most common sigma algebra is the power set, is the set of all possible subsets. Because imagine if I have a finite set and I assign probabilities to each element, if I want to have a probability assigned to having elements 1, 5, 6, and 8, I just add their probabilities. So if you have a finite set, this is not difficult at all. The sigma algebra has become very difficult as soon as you deal with infinity. This is the problem in mathematics. This is why you take classes in real analysis. It's to handle infinities well. And then, unfortunately, we cannot assign probabilities to every event. So there's a restriction. Now, for all practical purposes, it does not matter. You can get so many sets that you care about, it's fine. Omega is always going to be the outcome space. And then we're going to find a function, prob, because that's a really good name. When you look at it, you should be able to figure out what prob is representing. And it's going to take elements of the sigma algebra, and it's going to assign a probability to them. And the number is going to be somewhere between 0 and 1. So the first axiom of probability is the following. If you take a set in the sigma algebra, 0 is less than equal to the probability of A is less than equal to 1. So no matter how likely something is to happen, it will not happen with probability greater than 1. No matter how unlikely something is to happen, it will not happen with probability less than 0. Okay. Does everyone agree that this is a reasonable axiom? The key word is axiom. These are assumptions. These are the beginnings that we're going to base all of our theory on. The next one is the probability of the outcome space equals 1. Otherwise, it's not the full outcome space. The outcome space should list all possible outcomes of what you're studying. The last one is the more interesting one. How many of you have done geometry years ago? How many of you remember Euclid's 10 postulates? There's an old Sesame Street song, one of these objects is not like the other, one of these objects doesn't belong. If you go through Euclid, the first 9 of them are basically reasonable, and then the 10th one, or if you break it up into 2 sets of 5, the 5th one is just completely different. It's about 2 lines and another one intersecting and parallel stuff. And depending on how you take this, you either get plane geometry, spherical geometry, hyperbolic geometry. That's the one where the real action happens. Over here, this is the one where the action is happening. AI is an at most countable disjoint set of subsets of the outcome space. Then the probability of the union is the sum of the probabilities. This is the meaty one. What at most countable means is that the number of sets I have here is either finite or it's the same infinity as the natural numbers. I'm not allowing myself an uncountable infinity. If you don't want to write at most countable, if you want to write countable, we can just take a bunch of the AIs to be the empty set. But this allows us to phrase it in just one condition. I either have a finite union or I have a countable union. And then the probability of the union is the sum of the probabilities as long as they're disjoint. I clearly need disjoint if I want the probability of the union to be the sum of the probabilities. We saw before that if it was an uncountable union, that there could be issues with this. This is a very reasonable axiom to have for probability. That I want to assign probabilities in such a way that if my 2 sets are disjoint, then the probability that their union happens should be the sum of the probabilities. Does this seem reasonable? Okay, there are situations in voting theory where it turns out what you believe is a reasonable set of axioms does not lead to a fair way of creating voting. This is known as Arrow's paradox. I'll put up something about that. You cannot always assign things as your intuition would like you to believe. But here, this is a very reasonable one. We can do this. Now, you may notice that there are some conditions that I have not put up. So there are other things we could look at that we would love to see. So when we're trying to figure out, this is why I'm walking backwards because the camera is still having issues. We've got various sets here. What other axiom would you like to have, or what other result would you like to have that's not on this list? So, yes?
Some result about intersections.
Some result about intersections. So the problem is we have nothing here about intersections. So can we somehow deduce results about intersections from stuff over here? What else might we want?
Something about the probability of the empty set.
Something about the probability of the empty set. Okay. Anything else? So we want intersections, we want empty set. There's one other natural one, yes?
The complement?
So one is the complement. If I know the probability of A, I should know the probability of A complement. Anything else? There's one other natural one to me, it's the inclusion. If B is contained in A, should B be less likely than A? So to me, these are the wish list things you would want to add. So let's do empty set. So what do you think the probability of the empty set is? 0. Proof. The probability of omega union empty set is the probability of omega plus the probability of the empty set. So why is this true? Yes? The intersection is 0. So this is true since omega intersect empty is empty. All right, well, what's the probability of omega union empty set?
It's just the probability of omega.
It's just the probability of omega. So as omega union empty set is omega, we get 1 equals 1 plus the probability of the empty set. Therefore, the probability of the empty set has to be 0. So we don't need to have a separate axiom about the probability of the empty set. We get that for free from the other stuff we have. How many of you have taken a class in group theory or abstract algebra? Okay. I actually have to keep my hands down. I have never taken abstract algebra. Okay? I had to learn it, but I never was able to take the class. One of the things you learn in group theory is the definition of a group. There are 4 conditions for a group. Right? You have this closure, you have inverses, you have identity, you have associativity. One of the things I got when I was taking my general exam to get my master's is what happens if you have only a left inverse and a right identity? Is this still a group? What is the minimal conditions you need? Question on?
Yeah, sorry, what's after that omega?
Which? Get. So you can ask, what are the minimal conditions you need to define a group? Do you need to actually have both left and right inverses? Do you need to have both the left and right identity? Frequently, it doesn't really make much of a difference. You know what the identity is, the thing is commutative. But you can sometimes ask, what's the minimal set we need of axioms to work? We don't need to have an axiom on the empty set. We get the empty set for free from what we're doing. All right, so the next one is, now that we have the empty set, is to work on maybe the complement. So complement. So let's look at the probability of A complement. So what should that be? So it should be 1 minus the probability of A. And so the proof is, again, fortunately fairly straightforward. The probability of A union A complement, what does that equal? I'm sorry? Okay, good. So we can do it that way. Okay. So one way is to say it's got to be the probability of omega, because A union A complement is just omega. If you're not an A, you're an A complement. If you're not an A complement, you're an A, and you can't be both an A and not an A. Can we express A union A complement in terms of our axioms?
Well, it's equal to the probability of A plus the probability of A.
Good. So we get the probability of A plus the probability of A complement, because it's a disjoint union. And what's the probability of omega? That's just 1. And now follows from algebra. And so now we've shown that the probability of A complement is 1 minus the probability of A. That follows from our axioms. We don't need to include that as a separate statement. The last one that I want is the inclusion. So if A is contained in B, then the probability of A is thus equal to the probability of B. It feels like it would be absurd if this failed. I have a set of options. I have a bigger set of options. The probability my biggest set of options happens is smaller than my smaller set. But we need to prove this formally. So a good way to prove this is to look at what we have. We don't have much. We have the probability of the whole outcome space is 1. All right. We have any event has probability between 0 and 1. And we have the probability of a disjoint union is the sum of the probabilities. So the only thing that we really have to play with is we have probabilities of disjoint unions. So I have A and B. There's a third set lurking in the background here. What's the hidden set?
A not B.
A not B.
Union of like A and B complement.
So the union, you're close, but
Intersection
the intersection.
of A and B complement.
The intersection of A and B complement. Okay, so that would be the things in
so
A.
B and A complement.
B and A complement. So look at B intersect A complement. So these are things that are in B but not in A. So if you want, sometimes it's good to just draw things. So here is the outcome space omega. This whole set here is B. Here's A. And then this part over here are the things in B that are not in A. So this would be B intersect A complement. And then B would be the union of these pieces and it would be disjoint. So we can now write B is equal to A union, and I'll put this in parentheses, B intersect A complement. Why am I putting this in parentheses? I'm sorry? I'm treating this as a set, and otherwise I have to wonder, does it matter how I pass things? If I take the union and then I take the intersection, does that make a difference? And so I'm not going to get into that right now. I'll let you have the fun of playing with this and seeing, does it matter where you put parentheses? As a rule of thumb, put parentheses in. It minimizes your chance of making an error and just manipulating the algebra incorrectly. Well, now we know the probability of B is the probability of A plus the probability of B intersect A complement. And this follows from our third condition. We have a disjoint union. And now it's time to finally use the second axiom. We haven't used the second axiom yet. I don't think we needed to use it at all in the proofs of the first two things. But now we use it. By the second axiom, what do we know about the probability of B intersect A complement? It's between 0 and 1. So therefore, the probability of B is greater than or equal to the probability of A, as the probability of B intersect A complement is greater than or equal to 0. If this was a negative number, if this was, say, -5, then if we drop this, what would happen? So if this was -5, then the probability of B would be less than the probability of A. And so by dropping it, we'd have a problem. Because this is non-negative, if we drop this, the only thing we can do is either keep the right-hand side the same or make the right-hand side larger. And so you can see now the power of what we're doing. Is it all comes down to disjoint unions. if you have something that's not a disjoint union, rewrite it as a disjoint union. This is going to be one of the main techniques in studying things. Later on, we'll get to one of my favorite techniques. It's called the method of inclusion-exclusion. And it turns out that it's sometimes easier to calculate certain events than other events. We finally reached critical mass. We will be starting bridge lunches for people who are interested. Is there anybody here who has never seen a standard deck of 52 cards? Excellent. So there are 4 suits: spades, hearts, diamonds, clubs. Each suit has 13 cards. If you are dealt all cards in a suit, this is a phenomenal hand worthy of celebrating. Do you think this is likely or unlikely? Unlikely. You can in fact use stronger language than unlikely. All right. It is damn unlikely. Actually, even damn is not even strong enough. Okay. What about having 2 people at the table dealt all cards in one hand, in one suit? How do you think that compares to just one person? Now you have 2 people who are just getting one suited hands. Less likely. And you can even use stronger language. What about 3 people? Well, it's not impossible, but what do you think the difference is between 3 people and 4 people? I'm sorry? There's no difference. Because once 3 people have one suited hands, the 4th person has to have a one suited hand. So there was a bunch of people over the years who claimed that they were playing bridge, and everybody at the table was dealt all cards in one suit. And this happened multiple times in a 20-year window. What do you think? So you're shaking your head, you're suspicious? So one of the ways this was analyzed is people looked at how often people reported just 2 people at the table being dealt all of one suit. Do you know how many such occurrences there were in 20 years? None. But there were lots of occurrences of everybody at the table being dealt one suit.
Because they didn't shuffle.
So one possibility is they didn't shuffle right. And in fact, there's some great studies that went on that showed people were not shuffling the cards randomly. But they're shuffling enough so that you're not going to get these 4 suited hands. These 4 people each getting a one suited hand. But when you have unlikely events, look at other unlikely events around it. When we try to figure out what's the probability of this happening, it's often a lot easier to look at one specific person gets a one suited hand, and I don't care what happens to the other 3. That's a much easier event to calculate. And then we're going to use inclusion, exclusion. We're going to be trying to write things. The whole difficulty is dealing with intersections, dealing with complements. So we didn't formally derive the following, but let's see if we can. So we were talking about intersections. So intersections. So what do you think the probability of A intersects B should be from our discussions last time? This should be,
Are they disjoint?
no. If they were disjoint, it would be 0.
Right.
Yes. Almost.
Probability of A plus probability of B minus probability of A.
Right. You had things off by a minus sign, minus the probability of A intersect B. And so let's draw, our picture again of the universe. So here's omega, here's A, here's B, and here is A intersect B. Yes? A union B. Sorry, yes, this should be A union B. Thank you. Okay, so we want to calculate, so instead of doing intersections, I'm sorry, we should be doing unions. Sorry about that. Okay, so we want to calculate the probability of A union B. We have A here, we have B here, we have A intersects B here, and the union would be just this whole nice region. Now, of course, in general, it's not going to look as nice as this. This is just for graphical illustrative purposes so we can see what's going on. If I want to calculate A union B, if I take the probability of A and I take the probability of B, I've double counted the region A intersects B. So if I want to figure out what the probability of A union B is, I have to subtract the region I've double counted. Okay? Is this enough of a proof for people? Are people happy with that? Does that proof technically follow from the axioms? No. So what I will do is I will just sketch the nightmare if you want to make this truly rigorous. I could write this set as A intersect what? B complement. And I could write this set here as B intersect. So then I can write A union B as A intersect B complement union B intersect A complement union A intersect B. And now the probability of A union B is the sum of these three probabilities. And if I combine these two, I get the probability of A. And this is almost the probability of B. I need this again, so I add this again and then I subtract. So we do the trick of adding 0. Okay? I'm not going to bother going through the details. If you want to make this rigorous, it's a really good exercise to do so. This is the way it would follow directly from what's in here. Okay? And it's reducing our set to disjoint unions. Disjoint unions we can calculate. The probability of a disjoint union is the sum of the probabilities. And that's how we can proceed in something like this. All right, so we can essentially get everything we want from these axioms. So now the next one, I was jumping the gun, was trying to get to intersections. So intersections mean both events happen. Now the question is, how do you calculate the probability of an intersection? So how would you calculate the probability that A and B both happen? Is there a nice formula for this in terms of just the probability of A and the probability of B? At some point, you need to know what are your fundamental objects. What are the things you can work with? So here, we figured out how to do unions in terms of the original sets and intersections. You've got to be able to deal with either unions or intersections, and then once you have one, you can get the other. So one of the things I want to show you is the expected counts approach. And so let's let A be, to make sure, am I using, I think the coin had a 70% chance of heads? Yes. B heads on first toss, B heads on second toss. Tosses are independent. And you have a 70% chance of heads. So what should the probability of A intersect B? So can somebody tell me in words, what does A intersect B means happens? You get heads on both tosses. So what should that be? What should the probability of heads on both tosses? 0.7 times 0.7. And if we actually can multiply it out, it should be 0.49. And so here it's extremely important that the tosses are independent. If I had had a different coin for each toss and I had a different probability, it wouldn't be that problematic to figure this out. One way to do this is through the expected counts. So we can start off with some number of tosses. Let's start off with 1,000 trials. How many of those trials will have their first toss being a head? 700. So this is where we get a head, and then 300 times we get a tail. Now we toss again. How many of these 700 will have a head? I'm sorry? 490. And how many will be a tail? 210. And then similarly, if we come over here, how many of these will have a head? 210. And how many of these will have a tail? 90. So if we add all these numbers up, what should we get? We should get 1,000. Okay, it looks like it gets to 1,000. So we've started off with 1,000 trials, and we've seen how they fall among the different cases. The more options you have, the more painful this is going to be to do. For something like this, it's not too bad. And then I can look and I can say, okay, the outcome I want, the head, I have 490 out of 1,000. So head is, the A intersects B. I had 490 out of 1,000, so the probability was 0.49. Did I need to take 1,000? What could I have taken? 100. Why do you think I took 1,000? Yes? Decreases variability? So if we were actually to do numerical simulations, the 1,000 would be much more accurate. Absolutely. And the larger number we take here, if we do numerics, the more accurately that would come to the 0.49. But why do you think I'm doing this in class? Why am I using 1,000 and not 100? It's kind of hard because I'm supposed to be preparing the lectures beforehand. I'm writing the book, so I'm supposed to know what numbers work. Why would I choose something like 1,000? Yeah, it's to make the algebra nice. I may not know ahead of time with all the different fractions in play. I want to make sure all my numbers stay nice and integer. And so if I take something with a bunch of zeros, I'm going to be safe just by looking at what my probabilities are. I might be able to do something smaller, but I don't care. I want to try to minimize the chance that I will end up with something that's 49 2/3. And so if I just take a nice big number like 1,000, I'm in great shape. Okay. Any questions on this? This is a great way to segue into chapter 3, into the factorial function and the binomial function. When you look at these numbers, what do you notice? Anything interesting with these numbers? Yeah.
Two of them are the same.
Yeah, two of them are the same. We got them in different places. Do I have to include both of them? Can I just say, they're the same, so I only need to have it once? Okay, that would be very, very bad to throw it away. What this is saying is that if I only care about the number of heads and the number of tails, if I want to know having exactly one head, there are two ways of doing it. And both of those paths give the same number. And if I want to know the total number of ways to have one head, I just add these two. There's only one way to get all heads, there's only one way to get all tails. But there are two ways to get one head, one tail. If I were to flip the coin more often, I would start to have more and more possibilities. And depending on what you're asking, things matter. So the question is, does order matter? Is a head-tail different than a tail-head? Do you think it matters? So let's imagine you're in Vegas and you have $100. You bet $100 on heads. Heads comes up, you win. You now have $200. You bet $100. Tails comes up, you lose. You end up with $100. Or you get the tail first, and you have negative $100. You've lost all your money, you're now down to zero. You have no money for the next bet. If you're in Vegas and you're betting, the order in which things happen does matter. It doesn't matter how many heads and tails you have. It might matter the order in which the heads and tails come. So later in the semester, I might talk to you about how not to play roulette. So there is a strategy that a lot of people use in roulette called double plus one. If you make two unreasonable assumptions, double plus one is guaranteed to win and make you a fortune. These assumptions are unreasonable. Las Vegas knows that they're unreasonable, but they know that people are silly or don't know enough mathematics. And they will exploit people's lack of mathematical knowledge. The order in which events happen does sometimes matter. And you always want to ask, does it matter which way we do things? One of the biggest examples is when we're forming groups, are we forming say, student council, where all representatives are equal, or are we forming offices? Is the president different than the vice president? Almost surely. I don't know that many organizations where the vice president has the same power as the president. And you want to keep track of the order in which things happen. So I want to talk a little bit about basic combinatorics. So basic combinatorics. So the first is the factorial function. How many of you have seen the factorial function? Excellent. So what does 4 factorial mean? So 1 is 4 times 3 times 2 times 1. Another way is it's 4 times 3 factorial. So the factorial function is defined recursively. So n plus 1 factorial is n plus 1 times n factorial. And we need an initial value. What should the initial value be?
0 factorial 2.
So this seems like a very foolish thing to insist. So the factorial is you trial all the way down to 1. So 0 factorial equals 1. It turns out this is a really useful convention. It makes a lot of formulas significantly nicer if we just declare that 0 factorial is 1. We can interpret this. What does 4 factorial mean? It means if I have 4 people, I will assume the people are distinct, so they're not grad students. All right, 4 distinct people, and I want to order them. How many ways are there to order them? Well, I've got 4 boxes. I can put 4 people in the first. And once I've specified who's in the first box, I have 3 people left over for the next box. Then 2, and then 1. If you want, and I think I do this in the book, you can do the whole flow chart of writing all the different possibilities. Very similar to the expected counts approach we just did. It's painful. Okay, so this is saying that there's 24 ways to order 4 people when order matters. There would be 6 ways to order 3 people when order matters. There are 2 ways to order 2 people when order matters. There's 1 way to order 1 person when order matters. How many ways are there to order nobody? 1. There's 1 way to do nothing. You can't say, I could do nothing this way or I could do nothing. That's giving you 2 different ways of doing nothing. So view this as there is 1 and only 1 way to do nothing. Otherwise, you're doing something. All right, so we will hopefully accept that 0 factorial equals 1. Later in the semester, we will talk about a generalization of the factorial function that works not just for the integers, but also works for all real numbers. Also works for complex numbers. And we will eventually learn that -1/2 factorial is the square root of pi. This will be one of the most important calculations in the entire course. At this point, we have lost all connection to physical reality. So for those of you who are looking for things that you can point to in the real world, you will never, ever be ordering -1/2 of a person. Maybe half of a person if there's been a horrible accident. But you will not be ordering -1/2 of a person. However, mathematicians love to generalize. And it turns out we can come up with a function that agrees with the factorial function at the positive integers and makes sense at all real numbers, in fact, at all complex numbers for the most part. And it will have these wonderful interpretations. All right. So now what we're going to do is we're going to do a chain of different results in probability. So we've started with the factorial function. You know, how many ways are there to order? So now I want to choose k from n order matters. So if I'm going to choose k people from n when order matters, what must be true about k and n? Yes?
K is less than or equal to n.
K better be less than or equal to n. I should not be able to choose 15 people from 3. I probably also want k to be no smaller than 0. Okay. Later in the semester, we might talk about choosing -4 people from -8 people. But for now, let's confine ourselves to things you would see in the real world. I have 12 people. I want to choose 3 of them to be student council representatives. Okay? How many choices? So let's say n equals 8, k equals 3. How many choices do I have for the first? 8. Second? Third? So the answer is 8 times 7 times 6. It is amazing how many proofs in mathematics come down to doing one of the following two things: adding 0 or multiplying by 1. And I claimed earlier that there is only one way to do nothing. What's the log of 1? They're really essentially the same thing. Right? Whenever you have something in mathematics, always think about how can I make the algebra nicer. I'm pretty sure most of you have seen stuff like this before. I want to emphasize how you get to the nice clean formulas. This is a lecture on factorials. 8 times 7 times 6. This looks a lot like a factorial. What is preventing this from being a factorial? We're not going all the way down. So let's just go all the way down. Let's just put in a 5 factorial. What's wrong with this? Yeah, you can't just throw in a factor to make the formula nicer. At least not in this department. So if we multiply by 5 factorial in the numerator, what must we do in the denominator? We must divide by 5 factorial. And so if we do that, now everything is good. And now we've expressed it as 8 factorial over 5 factorial. And this is a much nicer way to represent the answer. And it all comes down to how can I write the answer in a good, clean manner. So in general, the solution is going to be n minus 1, all the way down to n minus k minus 1. So this is very similar to the birthday problem in terms of how far down do we have to go. If I want to choose k people, I go all the way down to k minus 1. So this becomes the same as n factorial divided by n minus k factorial. This is the number of ways to choose k people from n when order matters. I'm not sure if they still use this notation in high schools, NPK. Have you used this notation? I saw at least 2 heads shake, so okay. All right, so this is when order matters. What if order doesn't matter? What if I just care about who I have in my group, and I don't care the order in which they're chosen? So this is going to be the NCR, the combinatorics. And this one is a little bit harder. But in a lot of problems, this is the one that's going to be more useful. And if you think about it, when we did the expected counts, when we were tossing the coins, typically we don't care the order in which we get heads or tails. We just care how many heads did we get. So we want to know how many ways to choose k from n, order doesn't matter. So there's a lot of different ways to do the calculation here. The way I like is if order matters, we know the answer. So what's the answer if order matters? Yeah, just pointing over there. N factorial over n minus k factorial. I have a group of k people now, but they were chosen in a specific order. How many ways can I order k people? K factorial. So each of those ways is counted here. So I've overcounted my group by a factor of k factorial. So the answer is n factorial divided by n minus k factorial. What do I have to divide that by? By k factorial. Now, we normally write this in the denominator as n factorial over k factorial, n minus k factorial. And we have lots of notations for this. We might write this as nck, and we might write it as n choose k. So you read it as n choose k. Just so I know how much detail to get into, how many of you have seen these binomial coefficients before? How many of you have not seen the binomial coefficients before? Okay, so we've all seen this before. How many of you have seen Pascal's triangle? Okay, I will probably do some coding with Pascal's triangle just because there's a lot of very interesting mathematics lurking in Pascal's triangle. And in terms of what we're going to be doing, there's a lot of very important stuff to look at. So Pascal's triangle is 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. And I'll stop here. So these coefficients, this is what you would get if you expand out x plus y to the 4th, if you expand out x plus y to the 5th. This is one of the reasons why binomial coefficients are so important. You might have seen this in Calc 1 when you were taking the derivative of x to the n. You don't need the full strength of the binomial theorem. We will need that frequently in this course, so we will spend some time doing this. So what's one of the most famous results about Pascal's triangle? What pattern do you notice?
Powers of 11.
Okay, where's that?
So the 1, 11, 121, 1,331.
Oh, these are all multiples of 11?
The 11.
I don't think they're all multiples of 11.
Well, until you get to the two-digit ones, they're all powers of 11. And then once you get to the two-digit ones, if you carry the 10 digits over,
Okay.
they're all powers of 11.
So there is something special looking there, yes. That's a deeper one than I was expecting. So email me for that one. That is a good observation, but higher than we need now. If you add the two above, you get the one below, and you have ones going along the outside. So with those as the rules, everything is uniquely determined. So you just have this infinite string of ones, and then each one is you sum the previous two. So what I want you to get a sense of in this class is good ways and bad ways to prove things. To some extent, no matter how bad a proof is, if it's a proof, you at least have the result at your disposal. How many of you have seen a proof of this? I'm not seeing as many hands going up. So how many people have seen a proof that each number here is the sum of the two above? Wow, okay, not many. So I will start off with a bad proof. All right, so. And then I will show you a better proof. So, lemma. So n plus, see, it knows it's a bad proof, and the chalk was refusing to be part of this. N plus 1 choose k plus 1 is n choose k plus n choose k plus 1. Proof. N plus 1 choose k plus 1 is n plus 1 factorial over k plus 1 factorial n factorial. N choose k is n factorial over k factorial. Oh, did I make a mistake? This should be an n minus k. Factorial data algebra. And there's a proof. Just write down what the three things are. Expand. Sum. Simplify. Compare. And you're done. So if you want, you can go through and do the algebra. At the end of the day, will you have a proof of this relation? Will you have any understanding why this relation is true? I don't. If I go through this algebra proof, I have no idea at the end why this is true. What I want to do is I want to show you another way to prove results like this. So this is the proof by story. How many of you have heard the proof by story technique? Okay. What you want to do in combinatorics is the calculation you want to do is typically hard. So you show that your sum is equivalent to another sum, which is easier to do. So I'm going to do a warm-up, and then we'll prove that. So the warm-up, the algebra is actually not so bad. So lemma. N choose k is n choose n minus k. So the algebra proof is not so bad. N choose k is n factorial over k factorial n minus k factorial. This is the same as n factorial over n minus k factorial. Right? What's n minus k? K, right? And then over here, n minus k is the same as n minus k. And what's n minus k? That's k. So I just, oh wait, did I write k twice? I wrote k twice, sorry. So I have n minus k is here, and then, sorry. I just want to leave the n minus k as n minus k. Now I switch the order of the two factors. It's n factorial over n minus k factorial n minus k factorial. And by definition, this is n choose n minus k. So there's a proof. So I just rewrote k as n minus k, switched the orders in the bottom, and then notice that by definition. So again, lurking in the background is adding 0, doing nothing. Does this give you any idea of why this is true? So here's the proof by story. I have n people. Any Dr. Seuss fans? Anybody read the Sneetches? Okay, who are the best Sneetches on the beaches? Which ones? The ones. So there are two types of Sneetches on beaches. Those with stars on their bellies and those that do not have stars on their bellies. And the two groups do not play together nicely at first. The ones without stars do not get to go to the good parties. Okay? How many ways can I choose k from n to get a star? And choose k. If I'm choosing k out of n to get a star, that's the same as choosing n minus k not to get stars. So if I'm forming a group of k people, this is the same as saying I'm going to exclude n minus k people. This will be my loser group. Okay? So if you tell the story like this relationship is now clear. Okay? So what I want to do is I want to show you, we've got about 2 or 3 minutes left. I want to show you why the Pascal triangle relation is true by story. I need a good school. Wow. A good school, a good college. Williams. So we will have n from Williams. I need an academically challenged school. Amherst, thank you. We'll have one person from Amherst. All right. I want to form k plus 1 from these n plus 1 people. How many ways are there to choose k plus 1 people from n plus 1 people? N plus 1 choose k plus 1. Now there are 2 ways we can do this. We can be fortunate and not have the asshole, not have the person from Amherst, or we could unfortunately be saddled with the Amherst student. Do we all agree that these are mutually exclusive events and these exhaust all possibilities? So here is no one is Amherst. So how many ways are there to form a group of k plus 1 people from n plus 1 people if we do not have anybody from Amherst? N choose k plus 1. Because what we have to do is we have to choose k plus 1 people from the n people. What if, unfortunately, we do have that person from Amherst? Have the kid from Amherst. What will be the answer in that case? How many ways are there to choose k plus 1 people from n plus 1 if we have to have the person from Amherst? And choose k. And there's the proof. Much more enlightening than going through the algebra. So if we look at it this way, we wrote how many ways are there to choose k plus 1 people from n plus 1 people, and we broke it down into 2 cases. And we counted the number of ways of doing each one. And there's no double counting, because here we never have somebody from Amherst. Here we do have someone from Amherst. To be a little bit pedantic, it's actually better to write this a slightly different way. I would like to write this as 1 choose 0 times this times 1 choose 1. So I first choose no one from the group of Amherst, and then I choose k plus 1 people from the Williams. Over here, I choose one person from the Amherst crowd, and then I choose k people from the Williams crowd. So if people are interested, we might do a little bit more of stories like this on Monday's class. All right, so for next week, there's going to be no written homework assigned next week. This will be a chance for you to read ahead in the book and really build up your strategic reserve. We will be doing some programming. So I will want you to watch some programming lectures, and then we'll do some programming problems in class. This is the week to build up your strategic reserve. This is not the week to relax and say, no written homework. Okay, so use the time wisely. Homework is due on Monday.